Welcome back to another video in this multi-course trigonometric series explanation, where in this video we're going to be explaining the general functions of sine and cosine. To the upper right hand of the screen, you can see the general function of sine as follows: y is equal to a of sine theta, parentheses b of theta plus c plus d. Where in this video we're going to be explaining how each variable affects the graph of the function, and how each variable determines specific attributes of this function. So, from the previous video, which is going to be kind of like a part 2 series, we examined the graph of y equals sine of theta. And we deduced that the amplitude and period of this graph are 1 and 2 pi respectively. But how are we supposed to apply this knowledge that we learned in last video to this general formula? Well, that will lead us to the coefficients of a, b, c, and d's values or functions as per se, where I shouldn't say equal, sorry, because they do not have to have definite amounts, but as sort of a generalization for you, a's is the coefficient of sine theta's absolute value will give us its amplitude. And what the amplitude does it determines the highest value that the sine function can reach, or the lowest value that the sine function can reach. So, for example, for y of sine theta that we have mentioned earlier, we know the coefficient of sine of theta is 1. That means that the absolute value of 1 will give us 1 in this specific case, meaning that the sine function of y equals sine theta will could only reach the highest value of 1, meaning it cannot go to 2, the y value of 2, and it cannot go to the y value of 3, and so on. And likewise, opposite to that, y's value for sine of theta cannot reach below -1. That can be -2, -3, etc. So let us draw out y equals sine of theta, which might look something like this. With this, we lead off to b, which determines the function's period, which the period is defining by how many degrees will this specific length of the graph be repeated itself. So, back to the example of y equals sine of theta, we know the period is 2 pi. The period is 2 pi, meaning that for every 2 pi revolutions, this portion of the graph right here, which I'm going to redo in this pink color, this portion of the graph will repeat itself in both the positive and negative direction forever. And that is the period, essentially. And to find the period of a sine function, to the general function is y equals a of sine theta, parentheses b theta plus c plus d, will be deducing 2 pi over b. 2 pi for b will give us the period of the function. And what do I mean by that? And we can explore this in the specific example of y equals sine of theta. The b value, or the coefficient of theta, is 1. So therefore, we plug this back as 2 pi over 1 will give us 2 pi. 2 pi being our period, meaning that for every 2 pi revolutions, the graph of y equals sine of theta will repeat itself with this little snippet. And next up, we're going to be explaining the c variable. When the c variable is applied to a sine function, it determines the function's speed, which has to do with physics, and doesn't really have to do with a general knowledge of how to graph a sine function, but is necessary to understand a function's speed, as functions of different kinds do have speeds. C, when c is a positive value, will move the sine function left, while when the c is negative, will move the function right. So let us do a specific example down here, where we examine the function of y is equal to sine parentheses theta plus pi. Theta plus pi. So y is equal to sine of theta plus pi. Well, we know that if c, in this case pi, is positive, we will move the function left. In this case, we'll move the function left by pi. Or in general view, we'll move the function left by c, if c is positive. In this case, it is. So, as comparing this graph to y is equal to sine of theta, which we know with a general shape of about so like this, this function, our graph in red, will look something like this. Notice how it passes through the origin and it passes through the pi. This is pi right here. This point is pi. And this red function, y equals sine parentheses theta plus pi, will move faster than y equals sine of theta, as the red graph here is starting at an earlier point and moving at a constant speed relative to sine, whereas when this function right here has traveled pi distance, the y of sine theta has began moving. Therefore, this function is moving faster than y of sine theta by pi units. And other than that, we can move on to when c is negative, when c is not positive. So we can do an example of y is equal to sine of theta minus pi. Well, since pi is negative, we'll move the y equals sine theta's function right by pi units. Other than that, the function will remain the same and look the same as y equals sine of theta. As if we're going to draw this out, as I ran out of the room here, so I'm going to redo it here. Well, y is equal to sine parentheses theta plus pi. We will shift it right by pi units. So we will start at pi and go on. And that's one period. Whereas to the sine function, will look like this, which is in brown. The sine function will look like this. And in relating it back to physics, this function, which is in black, y is equal to sine parentheses theta plus pi, will move slower than the brown function of y is equal to sine theta, as this y is equal to sine parentheses theta plus pi is starting later. While maintaining a constant speed relative to sine of theta, it will be slower forever by a rate of pi, by units of pi. So y equals sine of theta plus pi will be always behind y equals sine of theta by pi units. And that, in general, is how you apply c to a sine function. Moving on to the d variable within the general function, which I'm going to rewrite here for the sake of visuals. B of theta plus c plus d. Now we're going to be focusing on d. D, just like how we would do for, you can think of this really as kind of like a parabola function, where ax squared plus bx plus c. C right here determines we shift it up or down. C determines the parabola shifting of up or down. Likewise for this, d will shift the sine function up or down, depending on if it's positive or negative, where if d is positive, it will go up, and if d is negative, it will go down. So let us apply this to a specific example for visuals and for conceptual understanding. I should do it by the line tool. Here, right here, where we're going to be labeling our axes, and for the specific function of y equals sine theta plus 1. For the original function of y equals sine of theta, we started at 0, right here. We started here and move outwards. But when we have y equals sine of theta plus 1, it will start at the 1 value right here. So it should be right here. It will start right here. Oops, sorry, that's poorly drawn, as this it should touch the x-axis, as we're shifting this entire function of y equals sine of theta up by 1 unit. So if you can imagine going on forever, likewise for the opposite direction, this will be moving at here, right here. If I could change the color, this function will be like this. Notice that the amplitude, when shifting it up by a unit, will be changed to 2, as the highest value that the sine of theta plus 1 function can reach is 2, not 1 anymore, as its middle value is 1. So that concludes our general function of y equals a of sine theta, or b theta plus c plus d. This concludes our explanation on the sine function. As the video is getting pretty long, I'll be delaying the general function of the cosine to the next video, where I hope that you have understood this general function of sine. Worksheets will be attached in the description below for you to practice. And as always, I hope you have learned something new, and I'll see you in the next video.